You know how your phone recommends movies, or how your GPS finds the fastest route? That's all thanks to algorithms. They're the invisible instructions secretly running our modern world. And today, we're going to pull back the curtain and see exactly what makes them tick. So let's start with a bit of a puzzle. What in the world could a brilliant mathematician from way back in the 9th century have to do with the supercomputer sitting in your pocket right now? The answer is pretty amazing. It's a direct line from ancient math to modern tech. The answer is this guy right here. Muhammad ibn Musa Al-Khwarizmi. He was a Persian scholar, and his work on calculation was so groundbreaking that when his name was eventually translated into Latin, Al-Khwarizmi became algorithmy, and from there, well, it evolved into the word we all use today, algorithm. And look, this isn't just some cool piece of trivia. It's actually the key to getting what an algorithm really is deep down. Think about this journey for a second. In the 9th century, Al-Khwarizmi is just writing down these incredibly clear step-by-step methods for solving math problems. A few hundred years later, his name, algorithmy, becomes the word for those methods. And today, it's this universal term for any set of instructions that solves a problem. It's an idea that's been cooking for over 1,000 years. All right, so we've got the history of the word. But what does algorithm actually mean today? Let's nail down a clear definition.
Okay, so the textbook definition is, an algorithm is a finite set of precise instructions for solving a problem. Finite and precise. Those are the magic words here. It means it has to end, and every step has to be perfectly clear. No guessworks allowed.
But honestly, the best way to wrap your head around it is to just think of it like a recipe. Seriously, a recipe gives you a list of ingredients and a finite, precise set of steps to turn them into a cake. An algorithm does the exact same thing, just with data and logic instead of, flour and eggs. And this is where things get really, really interesting. Because just like recipes, not all algorithms are created equal. Not by a long shot. Even if they get you the same result, the way they get there can make a world of difference. It all boils down to this one question. If you have two different recipes, and they both make the exact same delicious cake, does it really matter which one you follow? I mean, in the kitchen, maybe not. But in the world of computing, oh, it matters a lot. So imagine one recipe is the quick mix. It's efficient, the steps are simple, and you're done in 10 minutes. Then you've got the slow stir. It's complicated, messy, and takes a full 2 hours. You get the same cake at the end, but one of those recipes is clearly better. Algorithms are exactly the same. And this is where that difference becomes absolutely critical. Just look at the numbers here. With only 10 items to sort through, the difference is tiny, right? Fractions of a second. But what happens when you scale it up to 1 million items? The quick algorithm is done in 1 second. The slow one takes 3 days. That's the difference between an app that feels like magic and one that's completely useless. So how do the pros, the computer scientists, actually analyze and compare these different recipes? Well, they have a system. They look at how an algorithm performs in 3 different situations. They call them the best case, the worst case, and the average case. And together, these 3 scenarios give you the whole story of an algorithm's efficiency. Let's break them down real quick. The best case. I mean, it's pretty much what it sounds like, right? It's the absolute luckiest you can get. Imagine you're searching for something and you find it on the very first try. Bam! Done. That's the absolute minimum amount of work possible. All right, now on the flip side, you've got the worst case. This is the algorithm's nightmare scenario. It's when the thing you're looking for isn't even there, so the algorithm has to check every single spot before it can give up. This tells you the absolute maximum time it could ever take. But let's be real, most of the time we're not that lucky. But we're also not that unlucky. That's where the average case comes in. This is how the algorithm is going to perform on a normal, day-to-day basis. For the folks actually building the apps we use, this is often the one they care about the most. Okay, so to be able to talk about all this, to compare apples to apples, computer scientists needed a common language, a kind of official shorthand for talking about efficiency. What they came up with is basically a rating system. It's a way to classify how an algorithm's speed changes as you give it more and more data to work with. It answers the question, how much slower is this going to get if I double the workload? And this whole rating system has a formal name. It's called Big O notation. Now, don't worry, we are not going to do any math here, but it gives engineers a simple way to talk about performance. It's the universal language for explaining that huge difference between 1 second and 3 days. And all of this, the history, the definitions, the analysis, it all brings us to one last really important idea. Creating a great algorithm isn't some single flash of brilliance. It's a process. As you can see here, it's a constant cycle. It's not a one-and-done kind of thing. You design a solution, you test it out, you analyze how it performs in the best, worst, and average cases, and then you go back and refine it, starting the whole loop over again to make it even better. So, think about where we've been. We started with the name of a scholar from the 9th century, and we ended up at the very core of our modern digital world. These recipes, these algorithms, are the foundation of everything from your social media feed to groundbreaking scientific research. When you really stop and think about it, our whole digital world is built on these sets of instructions. Finding a better recipe, a faster, smarter algorithm can literally change the world. Which really makes you wonder, doesn't it? What's the next huge problem that a new, brilliant algorithm is going to solve?